One of the most popular, if not the most popular, recent ideas on the foundations of physics was just ruled out. It's the idea that entangled particles are actually physically linked by wormholes known as ER equals EPR. Let's have a look. ER stands for Einstein-Rosen bridges, which is the technical term for the simplest type of wormhole. EPR stands for Einstein, Podolsky, and Rosen, who wrote one of the first papers on quantum entanglement, though at the time it wasn't called entanglement. The conjecture says that entangled particles are connected by these wormholes. This idea was proposed by Juan Maldacena and Leonard Susskind in 2013. It's since become one of those phrases that theoretical physicists like because it's vague and sounds deep, but is hard to check. If you remember the infamous episode of a wormhole on a quantum computer, that was brought to you by ER equals EPR. The wormholes on the quantum computer were supposedly the entangled particles plus some higher dimensional blah blah, but let's not get distracted. The idea that entangled particles are physically linked by wormholes or anything is, of course, nonsense, because entangled particles are not linked. Entanglement is a sort of correlation. It implies no physical link whatsoever. A correlation just means that some observable properties are related. Identical twins, for example, share the same eye color. If you know they're identical twins and you know the eye color of one of them, you know the eye color of the other. That's what it means for properties to be correlated. Knowing the one will tell you something about the other. It doesn't mean they're physically connected. Entanglement is like that. You can of course say, look, we just take the mathematics for the entanglement and call that a wormhole. Okay, I admit this isn't wrong, it's just meaningless. I could also call my hair a non-perturbative field configuration, but it still wouldn't converge. If you want the ER equals EPR conjecture to be physically meaningful, then, you actually need some kind of wormhole there. If entangled particles are really connected by wormholes, then those wormholes should do something more than looking profound on a seminar slide. The authors of the new paper now ask a simple question. Suppose an electron is entangled with something else. If that entanglement is a physical wormhole and the electron has an electric field, then some of the electric field must go into the wormhole. Can we not measure this? At first, the answer to this question seems to be no, because whatever the wormhole, it's ridiculously tiny. Otherwise, we'd see particles disappear and reappear like popping in and out through portals. But the authors look at a case that we've measured very, very precisely. A hydrogen atom. A hydrogen atom consists of just one proton in the atomic nucleus surrounded by one electron. They both have a spin, and usually the electron and the proton spin are entangled. The authors now say that if the entanglement is a wormhole, then part of the electric field that spans between the electron and proton goes through the wormhole. That in and of itself is unobservable. However, if you poke a hydrogen atom with an electromagnetic field at the right frequency, you can break this entanglement and create an electron-proton pair that is not entangled. The author's point is then that these two states are now different. The one has a wormhole, the other not. And this makes a relative difference for the charge distribution in the hydrogen, which then makes a measurable difference for the energy levels of the electron. And this difference, isn't there. The electron energy levels of the two states, entangled and not entangled, are perfectly described by the standard quantum maths without the wormholes. Of course, this doesn't entirely rule out the idea. Strictly speaking, it just means that if there are wormholes, then very little of the electromagnetic field goes through them. So they say there's some parameter that must be very small. This is why I have to give the paper 3 out of 10 on the bullshit meter, but that isn't because of the paper, it's because the idea itself was already bullshit, so of course you can't rule it out. Now look, the people who work on this will say, but this is not what we mean by ER equals EPR. It's not a real wormhole, it's just a way to think about the maths. In which case, maybe you should stop calling it wormholes. It's quite easy to predict that this paper will not make a difference and physicists will happily continue publishing about this because it really doesn't matter at this point whether it's got any relation to reality. Still, I wanted to tell you about this paper because it's good to see that at least some people still treat the foundations of physics as the science it once was. In summary, ER equals EPR may be useful as mathematics, metaphor, or grant writing vocabulary, but as a physical wormhole, it appears to have the experimental visibility of my patience. Wild things have been going on in mathematics with the use of artificial intelligence. In the past months, we've seen lots of reports that AI is suddenly solving theorems that have been unproved for decades and making other advances. And on the one hand, we now have people who say that maths will be commoditized, as the current buzzword has it, that everyone will be able to do professional maths with AI. On the other hand, we have people saying most of these so-called proofs were just rediscoveries or actually wrong. What are we to make of this? I've had a look. This recent episode began in October 2025 when Kevin Weil, Vice President of Science at OpenAI, posted on X Twitter that GPT just found solutions to 10 previously unsolved Erdős problems and made progress on 11 others. This was then echoed by several other researchers at OpenAI. But what the hell are the Erdős problems? This is a list of about 1,000 maths problems, 60% unsolved, compiled by the Hungarian mathematician Paul Erdős in the past century. They're in areas like number theory, combinatorics, graph theory, set theory, and some other fields about which the average person says, wow, and then backs out of the room. There is no official list. There's just a website maintained by a mathematician, Thomas Bloom. So the Erdős problems are not like the millennium problems. They are mostly not considered to be of high relevance, and many have remained unsolved, not because they're so difficult, but because no one really cares. Still, it'd be interesting if ChatGPT had solved some of them. Yet it turned out that it had simply rediscovered solutions in the literature which had not been listed on the website. Thomas Bloom clarified, GPT-5 found references which solve these problems that I personally was unaware of. Demis Hassabis from Google DeepMind somewhat uncharacteristically commented, "This is embarrassing." Personally, I think that the OpenAI people should have checked themselves whether the proofs were actually known in the literature. All they had to do was to ask ChatGPT. But if even the guy who maintains the website didn't know of the proofs, it's still a pretty amazing search tool. There was another team of mathematicians who used ChatGPT to find a counterexample to one of the Erdős problems, but they noticed themselves it was a rediscovery of an earlier proof. We saw another proof pop up on the archive, which was suspected to be ChatGPT written and was swiftly withdrawn by the author. The OpenAI guys later deleted their posts, but you can see why the AI maths enthusiasm faltered somewhat during this episode. That wasn't all that happened though. We've also seen some examples where ChatGPT seems to have made a useful contribution to real proofs, albeit moderate and nothing of major impact. By January, however, ChatGPT did eventually also solve one of the Open Erdős problems, which Fields Medal winner Terence Tao called a milestone in the application of AI tools to these problems. So what are we to make of all this? One interesting thing that we're seeing clearly is that all these examples use ChatGPT Pro in particular, none of the other AI tools. This agrees with my personal experience. ChatGPT Pro is well ahead in maths compared with Gemini, Claude, and Grok. It's not a little bit ahead, it's a completely different level. In a recent report, OpenAI said they now have almost 1.3 million weekly users sending about 8.4 million messages on advanced maths and science topics, about half of which are mine. That's up almost 50% from last year. Topics include everything from analyzing data to debugging code to planning experiments. The other thing we're seeing here, I think, is some initial confusion confusion about the capabilities of the models and how to deal with them. AI models are extremely good at finding relevant information in the published literature. They sound somewhat lame and is the reason why there is a risk they just rediscover forgotten proofs, but it's also why they can help solving a problem, because maybe the solution is to apply some already known insight. And I think this is the stage we're at now. It's 2026, and the hottest new mathematical technique is finding the PDF. Will mathematics indeed become commoditized? I still think that with the current large language models, no. Again, I'm going here by my own experience. ChatGPT now does computation with SymPy, which avoids a lot of errors, but its logical reasoning continues to be weak. If it comes up with a proof, that's as likely to be correct as wrong. And I mean, it makes really idiotic mistakes, such as using a bound the wrong way round or just inventing a convenient assumption. At the moment, I think it's best understood as a discovery tool. But I actually do believe that mathematics will eventually mostly become something we can let AI do, and most human mathematicians will become obsolete, the same way that human calculators have become obsolete. And that will not be a minor change, but it'll take a few more years. And then mathematics will get a new research area called premium support. I am very fond of nuclear fusion. I honestly believe it's the energy source of the future, but it's not looking good. Nuclear fusion is in deep trouble. Let's have a look. In the past 12 months, multiple fusion companies have silently changed their plans or moved completion dates into the future. Zap Energy, for example, is a Seattle-based company that wants to use what's called the Z-pinch method to generate nuclear fusion. For this, one charges a huge capacitor and then suddenly releases the energy into the fuel gas. The electricity turns the gas into a plasma and creates lightning bolts that contract until fusion sets in, theoretically. In May 2021, they announced almost $30 million in funding and were, quote, targeting scientific energy break-even by 2023. Well, that didn't happen, did it? Then, just a few weeks ago, they announced that they're pivoting to nuclear fission. According to their website, today Zap is announcing that we're building not just a fusion company, but an integrated nuclear platform that spans both advanced fission and fusion technologies. Then there is Marvel Fusion, a Munich-based company doing laser-driven fusion with ultra-short femtosecond pulses. They've raised about 160 million euros, including from Siemens Energy and the EU Innovation Council. In March, they told investors they plan to sell their laser technology for defense, medical, and industrial uses. So not like they're giving up on fusion, but focusing on more immediate payoffs. They're also considering to relocate to the United States. I can't blame them. In Germany, if you want to build a laser fusion company, the first step is to fill out Form B377 for permission to think about sunlight. First Light Fusion, a UK company, has completely given up on their original plan. It started out looking good for them. They successfully demonstrated nuclear fusion by firing a projectile at a fuel target. In 2023, they signed an agreement with the UK Atomic Energy Authority to build a demonstration facility. But 2 years later, they published a strategic update that said they were discontinuing the proposed development to focus on advancing and commercializing its patented amplifier technology. Then they put out plans for a new demonstration machine with a vague completion timeline sometime in the 2030s, but also announced they'll be selling parts to other companies, which they started doing in April. So you see, there's a pattern here. Fusion companies shifting to selling related technology. The same thing happened with the Australian company HB11 Energy, which pursued hydrogen boron fusion. When they launched in 2021, they said their program is aimed at the holy grail of fusion energy research to demonstrate net energy gain. But in late 2024, they announced a shift to selling laser and target technologies. In their own words, because few private investors are willing to wait decades for a return. Then there are the companies that silently move their dates, like General Fusion. They're a Canadian company. In 2021, they announced they'd build a fusion demonstration plant in the UK with construction starting in 2022 and operations by 2025. Then the timeline slipped to completion in 2027. Then the entire project just disappeared. That's one way to reach confinement. They then instead built a smaller demonstration machine in Vancouver and now aim at a commercial power plant in the mid-2030s. Where does their money come from? In January, they announced that they plan to put out stocks by the middle of the year, and they're doing it via a SPAC deal with Spring Valley. That's the same company that brought NuScale small modular reactors on the stock market. If you don't know what a SPAC is, I talked about this in an earlier video on quantum computing. Basically, it's a way to circumvent proof of commercial viability. Then there is Helion Energy, which wants to generate fusion by shooting plasma rings at each other, and that is, among others, backed by Sam Altman. In 2014, they wrote on their website that they aim to have a commercial plant operational in 6 years. 6 years later, their plan was still to do it 6 years later. In 2021, they raised $500 million and said they want to generate net electricity from fusion by 2024. Then they said they are on track to generate energy by 2028, and now say somewhat vaguely before the end of the decade. The US company Commonwealth Fusion Systems said in 2021 they want to demonstrate net energy by 2025. Didn't happen. Their website now says it'll achieve net energy in 2027. Yeah, guess we'll see about that. You may have noticed a pattern here. It's that all these companies are American, British, or Canadian. This is, for one thing, because most startups are located in these countries, but it's also because companies elsewhere have been more careful with making promises. It's not that they're actually more successful elsewhere, it's just harder to pin them down on it. To top it all off, the authors of a recent study in Nature report that it's likely that even if nuclear fusion would generate net energy, it'd remain extremely expensive, even more expensive than nuclear fission. For the record, I think this analysis is too pessimistic because it's based on the cost trajectory of nuclear fission, which I think went badly for geopolitical reasons, not because of technological limitations. But Fusion Company have produced something commercially useful already: press releases with extremely high energy density. Thanks for watching. See you tomorrow.